So I've started the recording.
All right, so thank you for coming, Tyler. It's a pleasure to have you as in our group meeting. Just maybe for those who are listening in, we hope to stream our group meeting in the future, starting maybe next week. And we'll have I guess when we do the streaming, there'll be some announcements that like the YouTube will announce that that we're going to stream. So you can, if you subscribe to our channel, you'll be able to get those announcements. It's not because we're going to get a lot of people subscribing to our channel necessarily that we're doing that, making that statement. So let me turn it over to Gaurav, who can introduce our today's speaker for the group meeting. So Gaurav.
Yeah. Thanks, Michael. It's an absolute pleasure to have Tyler Cochran from Princeton University today at our group meeting. So I had the pleasure of working side by side with Tyler at Google Quantum AI on simulating Z2 lattice case theories. So Tyler is finishing up his PhD at Princeton with Professor Zahid Hassan, mostly focusing on ARPES measurements. And his research involves exploring Chern insulator in quasi-2D magnetic Kagome crystals and also in topological semimetals with protected band crossings. And his study also involves nodal line semimetals, providing the first experimental demonstration of linked loop quantum state. And more recently, his focus has been on the intersection between electronic correlations and topology. But he'll be talking about something different today, which is dynamics of excitations and strings on a 2D lattice case theory. And I must say that in addition to being a great scientist, Tyler has a great sense of humor, good taste in music, and is overall a great person to be around and to be friends with. Thank you for accepting our invitation. Tyler, please take it away.
Thanks very much, Gaurav. Thanks, Michael. It's nice to be here. Let's see. So I'm not able to share my screen. So maybe
Okay,
that's the first order of business.
Yep. Okay, so
that should be by the
you don't
share.
have the permission to. You don't have the permission to share. Yeah.
It says the host isn't allowing multiple presenter sharing for this meeting. Sharing is not turned on.
Okay.
And there's a little arrow button by your share button.
Yeah. Okay. Multiple participants can share simultaneously. Okay. Try it again.
Okay, much better. Let me. Okay, how does this look?
Beautiful.
Great. Okay. So as Gaurav said, most of my PhD here at Princeton has been doing work with photoemission spectroscopy and some scanning tunneling microscopy on real materials that have very complex Hamiltonians that we most of the time don't really understand very well. But today I'm going to be talking about my time, at Google Quantum AI, where I was a hardware resident and where I worked on visualizing dynamics of charges and strings in 2+1D lattice gauge theories. In general, please stop me if you have any questions. We can make this more of a conversation. But
group meeting, yes. In general, we'd love to do that, right? Hopefully. Thanks.
Yeah, great. Okay. So just a quick outline, I'll present the model that we're working with to simulate this Z2 lattice gauge theory using a toric code in a field. Then I'll just quickly say about one slide about what the superconducting quantum processor looks like and the hardware that we're using. And then after that, almost everything will be data. So it might look kind of pretty and it might look like simulation, but it is data, I promise. From the quantum processor. I'll give a brief description of the initial state that we start with for the quantum simulations, which is called the weight adjustable loop ansatz, or WALA. And then I'll talk about the different observables that we measured after doing Trotterized time evolution to probe confinement in the theory, to look at the string fluctuations in the confining phase, and ultimately the string breaking. So, this work's on arXiv. We posted about a month ago, so feel free to check it out, or, ask me any questions as well. Okay, so let me just give credit where credit is due. So everybody on the Google side was fantastic. Pedram and Abe led the project, and Yuri Linsky and Elliot Rosenberg provided a lot of really important feedback and technical support. As Gaurav said, the main work was done by the two of us. There's me. I took the honor of making a group logo for the Lawler group. There's apparently a law firm called the Lawler Group, so I replaced their little insignia with Cornell here. So from the Lawler Group, and we worked with Frank Pullman and Michael Knapp at TUM, and their student Bernard Jopes, and Adam Gibbon-Smith at University of Nottingham, and also Melissa at TUM. Okay, let's get into it. All right, so we're going to start by talking about this emergent Z2 lattice gauge theory, which is really a more generalized form of the Hamiltonian that you might see in Fradkin and Shanker, where let's go through each one of these terms individually, kind of pedagogically, so that we can understand what's going on. So we have this Hamiltonian where we have Pauli matrices that are defined on the vertices, these V's, and on the edges, these E's. And then you also have plaquettes, which are the product of edges not around a vertex, but around one of these empty sites. So, the vertices are here in green. So we're on a square site. These are like matter particles. We have plaquettes that correspond to magnetic fluxes. So here we have a mass term. We have the magnetic flux term. We have some dynamical matter coupling term in general here. And then you have something that looks like an electric field that's just sitting on the, what we call the gauge sites, the edge sites here. But then they add these two terms that are a little bit non-intuitive. So the first one maybe is this one. So usually in this sort of Z2 lattice gauge theory, you consider a specific gauge sector, and then you do that by looking at Gauss's law. So the local symmetry is usually this, in this terminology, XV AV, where A is the sum of X around the links. So let's see. So, we have one X here, and we have the 4 X's on the gauge sites around. And then usually we would, pick a specific gauge sector. We would say that all of these guys are equal to 1, and then we go forward. But here they enforce this kind of energetically. So we add this term, and then we also have a term that is a little bit strange in that it explicitly breaks that gauge symmetry if you had it. So we're going to start with this, more general, what these authors call emergent gauge symmetry. Sorry, emergent Z2 lattice gauge theory. Right, so we have, again, we're defining the plaquettes as the sum of Z Paulis around these magnetic sites, and these A plaquettes is the sum of X's around the vertex for this model. So once we have this Hamiltonian, we're going to take a limit. So we can either set, for example, J is equal to 0, and then we're working in the so-called toric code in a field regime, which is what we'll be doing. Alternatively, you can take HZ is equal to 0, then you're working in this kind of Fradkin-Shanker model where all of these guys will commute with the entire Hamiltonian, and yeah, you're left with the kind of the classic lattice gauge, Z2 lattice gauge theory. So we're going to take the limit of J goes to 0. When J goes to 0, these X of V's are going to commute with the Hamiltonian. All of them are going to commute with the Hamiltonian. So then the state will just be a product state between the gauge sites and the sites on the matter site. So we can completely kind of just forget about the matter sites. We set them all equal to 1, and then we look at just the dynamics happening on the gauge sites. And so then we're left with this kind of toric code Hamiltonian in a field where we have the sum of A operators, the sum of plaquette B operators, and then, local fields in the X and Z direction.
So the H's here, do they violate the gauge symmetry in this?
Yeah, so this HZ definitely does violate the gauge symmetry.
I think the other also, I think it also violates.
The other one, let's see. So here you have an X. In general, I think this term should commute with all of these guys because these guys are, sorry, I put the definition on this last slide, are also just X over E's. So it looks like this guy commutes with all of these guys. But okay, so in general, we are working in a model where
I like you with the B term.
the B term, you have the Z's.
On the same edge.
That's right. That's right. So this in general will, I guess the way that I think about it is this does give dynamics to kind of these magnetic fluxes. So yeah, in general, in the toric code, we think about these B's and these A's as stabilizers. But in this model, these aren't going to be steady. They will have dynamics, and so that an eigenstate of BP will not be an eigenstate of the problem. Okay, great. Any other questions? Okay. So the model is going to be this toric code in a field, which is sitting on this bottom plane on the left. I won't go into the details, but there is an isometry mapping that goes from this bottom plane back to the Fradkin and Shanker plane that looks like this. So in this talk, I'm really just going to talk about what's happening on this bottom plane. But in your mind, if you want to think about this isometry mapping back to the Fradkin and Shanker model, feel free to do that. There may be some caveats in that the entanglement spectrum is going to be slightly different, but the energetic spectrum should look the same. Okay, so now let me define everything really carefully with all the definitions that we'll use in this paper. So we have, the toric code Hamiltonian, which many people are familiar with, that has this sum over the AVs. I think maybe I flipped it from that last paper. So in this paper, these AVs are going to be the sum over Z around one of the matter particle sites. So here, this is the sites where these diamonds are pointing in and out, kind of going radially. Excuse me?
Should be product over the links instead of the sum, right?
You're right. Okay, good one. Yeah. So this should be a product here. Yeah, nice. Okay, so product over the links and product over the links here for BP. The B here is going to be sitting on the plaquette sites, which in this case are where these link qubits are going to be tangential. And it's well known that the ground state is this kind of equal position of all loops, of all Wilson loops. Then it has this sort of form. And in this paper from 2021, the Google group figured out how to efficiently prepare the ground state of the toric code. And so, as I said before, we're going to add these two terms that in general are not going to commute with the A's and the B's. And these we can think of as giving dynamics to the charge excitations and the magnetic charge excitations that live on the dual lattice. And we'll talk about this ansatz for an initial state in a second. Right.
So
okay.
the gauge symmetry in this Hamiltonian, right? In the second Hamiltonian is that that the placket term is equal to 1? Is that the gauge symmetry here?
So like I said, really there's no gauge symmetry here. Because we're working in this regime that has this term that explicitly violates the on-site gauge symmetry. But if you think about this isometry transformation, then yeah, I'm not sure exactly what the gauge symmetry looks like. But
yeah, I remember that you used the gauge symmetry for like post-selection.
So we didn't, I mean,
Right.
I'll talk about the post-selection. This is
Okay.
just kind of a trivial post-selection. There's no conserved quantity in this Hamiltonian that we're post-selecting on, but it's an artifact of the circuit that we're running.
Okay, thanks.
Yeah. Okay, great. So, just to pictorially show this, there was this previous work that was looking at the toric code, which is sitting at HM, HE is equal to 0. What we're doing in this work is looking at an extended region of this phase space where we expect to, close to this toric code fixed point, we expect to have a topological and deconfined stable phase with a transition around 0.3 for HM and HE. And past that, you expect a topological phase transition where you have a confined phase in a trivial topological order. And so the general approach will be to look at the dynamics of excitations that we initialize in the system to give a fingerprint for this deconfined topological phase in this confined charge phase. Okay, so we're doing this on the same quantum processor from this Nature paper from last year, where they demonstrated error suppression using the surface code. And typically, we're going to have what I'm going to be calling physical qubits, which is the qubits sitting on the links. These are the gauge qubits. Interspersed between all of these physical qubits, which are these green rectangles, there are also going to be ancilla qubits, which I'm going to use in the algorithm for the Chatterized time evolution. So these are not the matter site. They're really just ancilla qubits that are sitting there to aid in the time evolution. Right. Okay, great. Okay, so excuse me. So we're going to start with this weight adjustable loop ansatz. And that initial state has an ansatz form that looks like this, where instead of having an equal superposition of kind of the zeros and the flipped loops, like you have in the toric code, this quantum loop gas, you have a weighted quantum loop gas. And the intuition here is that certainly if you set theta equal to pi over 2, you expect this to be exactly the toric code ground state, which indeed it is. And so in the regime of HM goes to 0, this gives the correct ground state. As you take theta to pi over 2, this will go, sorry, as you take theta to 0, this will just go to the product state, all qubits in the 0 state. And so what we do is we optimize this theta value classically. And for our system size, which is 3 by 4 kind of charge plaquettes, these blue sites here, we get a curve like this as a function of HM and the Hamiltonian. In the infinite system, it turns out that there's a mapping that this maps to the mean field ansatz of the Ising model. So in the infinite system size, you get some flat state, you get some flat curve here, which corresponds to just maintaining the toric code initial state until some phase transition, and then you get this going down. So is this the ground state of this toric code in a field Hamiltonian that we're starting with? Here, no, it's not the ground state. But like I said, what we're interested in looking at is the initial state. And if we look at the difference in energy from the exact ground state on the system size, we see that it's very low. And particularly, it's very low compared to, say, the energy of one plaquette excitation, which is here one energy per unit cell. So, we expect this to be a decent low energy ground state so that we can initialize excitations on and then measure their dynamics. Okay, so we're going to be doing a Trotter expansion for the time evolution. So just to give a quick update on what that looks like. Generally, for the time evolution, you would want to have some unitary operator e to the minus iht. But here we're going to break this up into two parts that are mutually commuting. So for this torque code, all of the yeah, that's right. So for the torque code, all of these field terms can be applied in the same layer together in single qubit gates. And all of the plaquette terms can actually be applied in the same layer with the setup that we show down here. So essentially what we're going to do is we're going to sequentially apply H1 and H2 with small time step dt. So the algorithm looks something like this. We create this initial state here, which I guess I glossed over the circuit, but basically this is just taking the circuit from the previous work. So we can prepare this initial state pretty easily, and then alternatingly we'll execute the field terms, and then the plaquette terms. And the plaquette terms take 8 CZ layers. So basically we take these 4 qubit terms, we transfer the operators onto the ancilla qubits, we rotate the ancilla qubits, and then we spread the operators back to the physical qubits. So this is going to be the method for Trotterization here.
So just a quick question. So the number of qubits you need to add in, how many ancilla qubits do you have to add? 1 per unit cell?
That's right. So in this setup, it's 1 ancilla qubit per unit cell. And so, physical qubits for this setup, we have 17, and there's actually 18 ancilla qubits. You can imagine not having the ancilla qubits. And then indeed, you can do better in terms of number of qubits. And in this case, like I'll show, it's actually slightly convenient to have the ancilla qubits because we can post-select on them after we have done, n number of Trotter cycles or however number of Trotter cycles we're interested in. And that post-selection actually turns out to be helpful. Which is what I show on this slide. Perfect. So, okay, so here I'm just showing, okay, so if you look at this circuit long enough, you can convince yourself that at the end of a Trotter cycle, the ancilla should be completely decoupled from the physical qubits. And indeed, if there are no errors, they should return to the 0 state after these plaquette terms are put in, are executed. But of course, on the device, we have noise. We have all sorts of coherent errors going on and incoherent errors going on. So if we look at just the expectation value of Z on all of these ancillas, and here I guess I'm measuring the probability that Z has gone from 1 to -1, the expectation value. You see it increases as we increase the number of Trotter cycles. And it's increasing, and it seems like it's tending towards 0.5, which makes sense because this would be like, the maximally mixed state. So we tried a number of things, but the eventual strategy that we settled on for the paper is just to post-select on bits where all of the ancillas are in the 0 state at the time of final measurement. So this doesn't scale particularly well. Here, in order to get a decent number of shots for an increasing number of Trotter steps, the total number of shots on the hardware that we have to take scale something like 2.5 to the number of Trotter steps. So this is an exponential scaling. So for the latest times here, which correspond to about 9 Trotter steps, this corresponds to about 1.5 million shots on the hardware to get out roughly, well here in the gray, it looks like we're getting about 1,500 shots. Additionally, later we actually post-select on the number of plaquette flips that we have. So basically, this is about 300 to 400 shots constantly with this exponential scaling. So this isn't great, but this is what we're doing, and maybe in the future we can think about some error mitigation to improve the scaling.
How long does it take to take 1 million shots?
Yeah, so so when you're in this regime where you are running the same circuit, everything that you put on the FPGA is the same, you're just running it many times. So there's a little bit of a bottleneck sometimes on some systems uploading multiple circuits to the FPGA. But here, we're taking 1.5 million shots on the same circuit. We also have some randomized compiling. So, we do really it's 1.5 million shots times like 30, so maybe 45 million shots. But the rep rate in that sort of situation is close to 100 kilohertz, maybe 50 kilohertz. So, on the order of 15, 20 seconds.
15, 20 seconds to do 1 million shots. That's awesome. Okay.
That sounds right to you, right, Garo?
Yeah, I'm not sure.
Well, I guess, if you could do it, if you could do 1 million shots in 15 seconds, maybe you could have run longer. But maybe going to the next data point, it would just be like a day.
Yeah, you can always think about going farther. Here, what I'm not showing is that we're interested in many different Hamiltonian parameters. We're also doing error mitigation in the form of randomized compiling. So there are other multiplicative factors that make that 1.5 million, quite a bit more for the specific physics that we're looking at.
So what is the data rate that you're saying? 100 kilohertz?
Yeah, that's right. Yeah, I think that's kind of the limit.
Yeah, I mean,
And
like the number checks out, but I think like as you have like longer circuits, right? As you have deeper circuits, right? Like the numbers significantly add up because it takes like a significant amount of time to like run a deeper circuit compared to just like taking.
yeah, that's actually true. So so on the superconducting processor, right? Like one thing that you're limited by is resetting all the qubits to the zero state. So this like fundamentally at least sets the repetition rate. And then this is on the easiest way that you can do that is you just sit and wait with the qubit having some coupling to the resonator. You just sit and wait, and then eventually it will decay to the zero state because it's energetically favorable. So then you're kind of set by this T1 time, right? But you're right. So some of these circuits none of these circuits are longer than T1. But they're coming to be a significant fraction of T1. So then, yeah, maybe it will be a factor of like at most 2, right?
Yeah, that's right.
Extra time for the longer circuits. Yeah, good point. Okay, great. All right, so let's do some of this dynamics, and let's start by looking at the confinement of charges. So we're going to start on this grid that I showed before that has on the charge sites 3 by 4 sites. And after we prepare the Walla initial state, we're just going to put one X gate here. And if you'll remember, these charge operators are the product over Pauli Z's. And so if we have one X site on the qubit between 2 charge sites, this is going to flip the expectation value of this A plaquette on the 2 neighboring sites. And so we're going to call these our charge excitations. And we're going to start with an initial state here on the left of these 2 charge excitations, a distance 1 apart, sitting in the middle of this grid. Now what we're going to do is we're going to run the trotterized Hamiltonian for different values of HM, which is like the magnetic field, and for a fixed value of HE, which as I look around, I guess it's actually not on this figure, but HE is 0.25. And so this HE, let's actually go back to the Hamiltonian just so that we can all look at it. This HE is Pauli X. So in general, this is going to give some sort of hopping dynamics to the charges, which we're calling A's. And this HM is what we're going to vary to kind of go through this phase transition. So really, we're going to be exploring a line here at many different HM values at constant HE. So we start in this topological phase and we move into the confined phase. Okay, great. So that blue color scale going from blue to black corresponds to this value of the magnetic field, which should be the confining parameter. And when we look at the raw data for the distance between these two particles, so what we do is we run some trauterized time evolution, and then we look at the distance those two particles have traveled. And for the deconfined phase, we see it increases kind of linearly, and eventually, we're at a finite system. So if we went to much longer times, we would eventually start seeing this thing bounce off the edge, and then the distance would come back in. But in this time regime, we haven't reached there yet. The distance between these guys is still kind of increasing linearly. And we see as we ramp up this HM, when we ramp it up a little bit to 0.3, almost nothing happens. When we go farther, we start to see that this comes down, the slope comes down. And then even more so when we go to 0.8 and when we go to all the way to 2.0, the slope has decreased a lot. But naively, if you just look at the raw data, it looks like this is still increasing almost linearly. Maybe there's a little bump here. But the other thing that we can do is we can start with this setup, and we can actually evolve under the Hamiltonian that has HE and HM set to 0. So in that case, this should just be a stationary state of the system, and you expect no dynamics. So you expect, everything just to sit there if you didn't have any errors or decoherence going on the device. And that's what I show here by this gray bounding region. And in the later figures too, I'll show this kind of decoherence limited region by the gray bounding region. And there we see also the distance between these two particles is increasing. So this is just increasing because there's noise on the device, there's T1 decay, we're doing a lot of CZ gates, which are adding decoherence. We're doing randomized compiling, so we can hopefully approximate these as local depolarizing channels for the CZ error. But in principle, even in the ideal situation, we're seeing these particles run away, so we can just do something very simple, and we can approximate this error model as a global depolarizing channel and just use that to rescale the data. And when we do that, we get this bottom panel, which is the depolarization mitigation, as I label it. And then when you compare this to an exact circuit simulation, which are the line, now the agreement looks very good. So this is kind of a phenomenological error model, if you like, but it works very well to compare the device data to the numerical simulation. And we see a bunch of cool things, right? We see, for one, we see this kind of linear increase for the low value of HM. We see that as we increase HM, we're getting this turning over, and we're actually getting this turning over before we would reach the value that you would expect just for the thing bouncing off the wall and coming back. So this, even at 0.8, this seems like the excitations are maybe spreading, but then coming back together or having some confining potential before they've had the chance to completely bounce off the walls. And then once you really ramp up to a large confining parameter, 2.0, we see it sticking very close to its initial separation of 1 apart, and even maybe a little oscillation. And you expect this oscillation in general. Just think about like block oscillations. You should have some, you have a periodic potential. You should have these particles having some sort of oscillation back and forth. And indeed, we see that. So this is great. Here on the right, We also, we're measuring each of these A terms individually. So here I'm showing their average separation, but we can, measure the expectation value on all these sites. So if you don't like this picture, maybe you can just have have this one where seeing is believing, where you have the deconfined case, and as you look at different time steps, you start the excitations one apart, and then after time 3, they've kind of completely explored the lattice. Whereas for HM is equal to 2.0, you start them next to each other, and then by 2.7, the probability that they're still sitting next to each other is very high. Yeah.
So at HM equals 0.8, the idea that they might not actually make it to the edge and come back, is that in the theory? Like, is HM equals 0.8? Like, if you solve it, not on the simulation, but like in the maybe classical simulation, that the plot you're showing, the solid line in the plot you're showing, yeah, that's in that calculation. Does it do that? Is it confined? Is it in the confined phase at HM equals 0.8?
Yeah. Yes. So it's in the confined case, but it's in the confined phase, but it's a little tricky because the system is so small that the kind of the phase transition is significantly broadened compared to the thermodynamic limit. So indeed, if you looked at this sort of circuit simulation going a long time out, what you see is you see some oscillations that happen, but it never, the distance between the two excitations remains less than, in this case, what you would expect for the maximally mixed state with this projector onto the two particle sector, which gives you an expectation value of 2.3, I think. So what you can do is you can look at this value of 2.3 and you can say, are the excitations ever there? So I actually don't have that sort of long time circuit simulation in this slide deck, but indeed there are signatures of this confining these confining dynamics for 0.8.
Thanks.
Yeah, that's important. Good one. Okay, so we have a fancy digital quantum processor. You can think we can probably do something more interesting in terms of starting with a more interesting initial state and an initial state that's slightly closer to something that you could imagine physically. So physically, if you had two excitations and they're in a bound state, you can imagine that they're probably going to be in an angular momentum eigenstate. So we don't quite have a large enough system to do that, but what we can do is we can start in this superposition state where we have an excitation on these diagonals and these diagonals, and we either have the superposition state of this guy plus this guy or this guy minus this guy. And then you imagine that there's probably going to be some interesting quantum interference effects that are coming from this superposition initial state. And so we can do this, right? Okay, so I don't have on this slide, but if you're interested later on, I have a slide that talks about the circuit that does this. Basically, we prepare a mixed state of the system. If you don't consider it coupled to an ancilla, but we have an ancilla, and then based on the measurement of the ancilla qubit that we do at the end after the trauterization, it projects onto either this plus state, this plus this, or the minus state, this minus this. And so when we look at the dynamics of the minus state and the plus state, they start with an initial separation of 2. And when we have HM is equal to 0 in the deconfined case, these guys run around. They do distinct behavior. In the plus state, they're able to kind of come closer together as an initial step. So you see them come closer together, but then eventually go off to explore the rest of the lattice. In the minus state, they're not able to come closer together, so they immediately come apart. And we also see that. So initially, we were thinking of this as kind of a way that we can make the dynamics happen faster, to push these particles apart faster. And indeed, that works. But for this HM is equal to 2.0 case, here we see the separation between these two particles stay really close to 2. For this entire time. So here, these guys are sitting there. Maybe there's some maybe, they're on these sites or these sites, but the separation is really at 2. And we can, look at kind of more fancy observables where we're doing this conditional probability, where we say, okay, if we measure one on this guy, where's the other one? So in here, I'm just showing for the minus case, this guy minus this guy. If we have a particle on this site, then the other one is kind of spread to this corner. If we have one on this guy, the other one is spread to this corner, et cetera, et cetera. And then in the confined case, really, you only have significant probability of the particle sitting on their initial states. When you look at when you condition on the corner, you have a very small probability that the particle is there, here on the order of like 6% chance. But, the other particle is very preferentially measured on the site 2 away, corresponding to the initial state. So this is the time evolves state after t is equal to, I think, 3.5. So where this kind of separation between the plus and the minus state is close to maximum. Okay, so
So
yeah.
for the initial state preparation, right? So you defer the projection onto the plus or minus 1 eigenstate all the way to the end, right? You do all the measurements at the end, and depending on the result on the ancilla, you consider that to be a plus initial state or a minus initial state. Is that correct?
That's right. And then we just kind of, sort the bit strings into two batches.
Got it.
Yeah. So, yeah, conceptually, maybe it's more convenient to think about doing that measurement immediately mid-circuit, and then evolving from there. But, on the device, that takes on the order of like 10 Trotter cycles just to do the measurement, because the measurement is very expensive. So it's much easier to do the measurement at the end and then just use it kind of as post-selection. Yeah. Okay, so the takeaway from this slide is that we're measuring the dynamics, and we're measuring these charge operators, these product of z's, and measuring these charge operators, we can see this difference between the deconfined and the confined phase. So now I want to, okay, yeah, maybe I'll show this kind of fancy picture. Okay, so now I want to present the same physics with a different observable. Let's see how we're doing. Oh, wow, okay, I need to hurry up. So we can also look at these kind of X strings. So in this model, you expect that you have 2 charges, and in the confined case, these are connected by a Wilson string. So the string of X's corresponding to the path between these 2 particles. So back here, you can see this is how we actually initialized the state. We had an X gate here, and so we had the string connecting these 2 particles. In the deconfined case, though, actually the state that you prepare when you, for example, had X gates going from here to here, is degenerate with it's a superposition of all such paths that connect, all such Wilson strings that connect the 2 particles. So basically, you would imagine that these strings are not physical in the deconfined case, but in the confined case, they are physical. So what we're going to do is we're going to measure this 2-time correlator, where you have X on 1, which is this qubit here, or this qubit here, at time 0, and then we're going to measure X of 1 to J, which is extending out to the right, at time t. And we're not going to perform the local fields on this one special qubit. So one of the excitations is just going to be sitting off here at the edge. It's going to be pinned. There are going to be no terms in the Hamiltonian that will let this guy walk into the lattice, but the other particle is free to run around. And just to quickly show the results, when you're in the deconfined phase here on top, this is HM is equal to 0, we see that very quickly this expectation value of the kind of x1 of 0, x1 at t decreases down to a very low value, and we get some probability of measuring the longer strings at later times, compared to at the confined case. For the confined case, we really get very little probability of measuring the longer strings at later times. So in the interest of time, I won't say a whole lot more, but we have these complementary ways to measure the confining dynamics of the charge excitations. We can either measure the charge operators, these A sub V's, or we can instead measure the Wilson strings to get to the same sort of physics that these guys are either staying close together or they're running apart.
Give me a quick question. So when you're measuring these strings, is it noisy? Is it a lot harder to measure in the string operator than say?
Right. So in general, it's not any noisier, I would say, than the charge operator. But I mean, here you can see maybe again, we do the same trick where we measure an eigenstate and we look at how fast that eigenstate decays, to get this decoherence-free region. And this is decaying quite a bit. So this is showing that there is a lot of noise in the system. But in the confined case, the signal is really staying close to this sort of decoherence limit, whereas in the deconfined case, it's going to zero very quickly.
And in these plots, is the solid line just connecting the dots, or is it the classical simulation?
It's just connecting the dots. Somewhere I can find it for you if you're interested in the value of the classical simulation. It's in the SI of the paper and in a later slide, and kind of the extended slides. But it matches very well. But these are just connecting the dots. Yeah. Okay, great. So now that we have this concept of the Wilson string, and we know in the confined case that the Wilson string should be physical, we want to actually measure its fluctuations. So the first thing that we do is we start with this Walla initial state, which here I'm labeling as the vacuum, and we are going to put a string across this initial state that has a bump in it. So we apply this initial excitation, which is this string of x's, and then we expect to have an initial string that looks like this black line. And we're going to play the same trick where we're not going to apply local field terms on this qubit and this qubit. So the excitations are really going to stay pinned to the edge. You're going to have a string connecting them, and then you have a little bump in it. So naively, you would think maybe it's going to vibrate. It's going to do some whatever dynamics are allowed by the Hamiltonian. And in particular, there is this kind of breathing mode where the string is going to undergo these sorts of dynamics where it just kind of goes out and in. And in this way, you can see the length of the string doesn't change. So if I come from a string that is going straight across here to a string that is first going up and over, the total number of gauge qubits that it traverses from the left to the right side will be the same. If you go from the top to the bottom, of course, the initial state and the final state will be the same length. But the catch here is that there's no term in the Hamiltonian that directly couples this guy to this guy. So you can imagine them going through like a virtual state in the middle that has a different length. And that kind of virtual process of going through the different length is going to be suppressed as we go to very strong confining potential, because then you have a large energy term associated with each link qubit, each qubit on the link. And so we expect in the very confining case, we're primarily going to just have this breathing mode. And then as you approach the confining potential, the transition point, we should start to have these kind of flopping transitions where the string is vibrating back and forth. And then in the deconfined case, this notion of a string really isn't even well defined. So we're going to measure this kind of wacky observable to look at these dynamics, which is the correlator between z on a qubit at time t and time 0. And then we're going to multiply this by the expectation value of z at the beginning. And so basically, because the X string will anti-commute with Z, this is giving us, this first part is giving us some information if the string has come or gone compared to its initial state. And this final term is giving us something about whether the string was there at the beginning. And so we put them together and we can really image the string dynamics. So the results are here in panel C of this S sub ZZ observable. And the deconfined case here, HM is equal to 0.1. Even at time 0, when we measure this guy, we don't see the defined string that we started with. And this is related to the fact that the string is really not well defined in the deconfined case. And so, as soon as you apply 1 or 2 Trotter cycles, basically everything looks homogeneous on the system. If we go to the other regime, now in the confining case, I'm using HM is equal to 1.4. This S of ZZ indeed shows the trajectory of the string that we started with, going from the left to the right-hand side. And we see this breathing mode that I described earlier, where as you evolve in time, the string probability comes out to the edge, but then it primarily comes back to the center after some time. But then the probability that it comes to the bottom side is pretty small. So, okay, maybe it was a judicious choice of color bar, but when you compare this to this kind of weakly confining regime at HM is equal to 0.6, here we definitely see these sort of flopping transitions where the string comes down and has some probability of being on the bottom side after some given time, 1.2 or 2.7, with some decently high probability. So I think looking at these pictures maybe is enough. Here I'm plotting for specific qubits, Q1 and Q2, this observable. And indeed, this shows that kind of in this HM is equal to 1.4 regime, all of the signal that we're seeing on the bottom can be described just from decoherence on the device, similar to what we saw before. But on the top, we're seeing kind of go towards 0, some, probability that the string is there and not there. So we have these strong signatures of the string dynamics and this changing of the string dynamics as we go close to the confining transition, where we're going from these primarily breathing modes to more modes available that are kind of higher order in perturbation theory. Cool. Okay. So I'll just quickly show. Oh, yeah. Maybe this is a nice. You can see the actual dynamics that we measure here. So the last part is that by going back to this picture of measuring the charges, we measured the charges, we saw confinement, we measured the strings, we saw confinement, we measured the strings and we're able to visualize the dynamics of the strings. When we go back to measuring the charges in this setup where we had the strings, and we turn on a large HE field, in general, this term in the Hamiltonian is able to break the string. And so we know that the string is localized on the top qubits from what we saw in these confined dynamics when HM is equal to 1.4. And when we look at where we're getting pair creation, where we're getting extra particles, when we do the time evolution, we see primarily they're popping up on the top qubits and not the bottom qubits. So here, for example, for HE is equals 0.5, in yellow, I'm plotting the top qubit. In green, I'm plotting the bottom qubit. And in black, I'm plotting if I didn't have a string going across the system to begin with. And indeed, we see a lot more particles popping up on the top compared to on the bottom. And when we vary HM in this case, we actually get a resonance when HM is equal to 2J. And this is when the energy of having 2 particles be created is equal to the energy of flipping one of the gauge sites or breaking the string. So again, this is exactly what you would expect here, that around HM is equal to 2J, we have this resonance in this in the string breaking by looking back at the charges. Okay, so that's it. We talked about the state prep, the particle confinement from two different perspectives, then looking at the string dynamics and the string breaking. Going forward, I think there are a number of things that we can do. We could explore this phase diagram that I showed at the beginning a little bit more, adding dynamical matter degrees of freedom, like similar to what was done in Garov's paper on disorder-free localization. Our collaborators from TUM have some nice ideas about compressed circuits, which they describe in this PRX quantum paper to maybe have a more efficient time evolution, for example. And there are also from Nathan Weba's group, there's some idea of hybridized lattice gauge theory simulation and error correction, because the circuit looks very similar to the surface code circuit. So you can imagine maybe some interesting kind of hybrid where you're doing error correction on a model that's suited for it. And so maybe you can get some gains there. And then, in parallel, people in Chris Monroe's group, also Peter Zoller's group coordinating with QERA have done similar things. So the QERA paper is not posted yet, but I think it will come out this week. And the paper from Duke was posted last week. So, there's a lot of excitement in this simulation of strings and string breaking, for example, in Z2 lattice gauge theory. You can tell Garov and I are excited about it. Maybe Subir, Igor, and Vadim are more serious. But in all, it was a great experience to work with Garov and to work with everybody at Quantum AI. And yeah, thanks very much for having me at your group meeting.
Thank you.
Thank you, Tyler.
Yeah.
So any questions? Well, maybe while you think, let me make a comment and then maybe an odd question too, and then maybe other questions. So first comment was, I think you're working with so at the beginning you mentioned when you were describing the Hamiltonian and everything, I was confused still about the role of gauge symmetry, but it felt like at some point you fixed the gauge. Is that right?
That's right. Yeah. I mean, so
once you fix the gauge, and then you turn on the HM and HE fields in the fixed gauge scenario, right? Then everything kind of makes sense to me. If you go back, unfixing the gauge from there, then those terms, HX and HT, those things will probably become, those will become gauge invariant terms. Right, so like if you go back to the, you actually have a Hamiltonian which is fully gauge invariant always. I think that can explain why there might be this isometry with the Shankar case. Because once you fix the gauge, now you're working within a fixed gauge kind of situation. I think that everything made sense to me after I realized that.
yeah.
Okay, so if you agree with that statement, good. And,
Right. Yeah. I agree.
And then the second, I guess my main question is, what is impressive to you about what's been achieved here? So classical simulations are basically reproducing a lot of what you've done, as far as I can tell. But like you didn't give us quite an impression about how close are you maybe to say quantum advantage in these kinds of things?
Okay, yeah, great question, and thanks for asking it. So you're right. I mean, maybe we can look. I didn't show classical simulation for everything. If you dig into the details of the supplement in the archive posting, indeed, you will see that for everything we do, I can run a exact circuit simulation of that, which is even worse. It's not like even we're resorting to MPS or DMRG or something to compare on the classical side. I think just what is important and impressive here is the ability to do the time evolution with these kind of high weight terms. So these A's and these B plaquette terms are not completely straightforward to implement on the hardware. And indeed, you see, this is 8 CZ layers which, theoretically it's very straightforward, but actually we're limited. We're right on the edge of what we can actually, of whether we can say anything. You can imagine if we only had half the number of Trotter steps available, very quickly you would have no contrast. And if if we had more, then we start to get into edge effects. So we're kind of right at the sweet spot. But to be able to actually implement this sort of 2D lattice gauge theory, this 2D toric code evolution, I think is a big deal. And I hope that what this will be able to do is eventually open the door to study maybe more complex gauge theories, like I said, maybe with dynamical matter, where there might be something that's computationally hard. For this model specifically, I think in general, it will be hard to get some sort of a quantum advantage, but there's a lot of interest in studying gauge theories in general. There are interests from the high energy people to study, for example, quantum chromodynamics eventually on quantum computers. And, this is a long way from there, but we show that we kind of have all the building blocks for studying this confinement problem in this simple model, and that it works out on the quantum computer, even with all the decoherence.
You have these high terms. That's what makes it hard from a quantum hardware perspective. But from a classical simulation perspective, it probably isn't a big deal. So
that's right.
More balance than we might have expected. That it's a little harder for quantum hardware to carry this out. Actually, I think Gaurav mentioned that nobody's done this before. Is that right?
That's right. So this paper from the Google group, and then these papers that are coming out now. So this paper from Chris Monroe's group is actually still on, let's see, this one that posted last week, it's still on 1+1D. And soon there will hopefully be a posting by QEra, which will be, also 2+1D. But that's right. So this is the first 2+1D. And then also, this is, I think, the first time of actually measuring these kind of string dynamics directly, which you kind of need 2+1D in order to do, because if you have 1D, the only thing the string can do is break. It can't wobble around. So that's right.
All right. So while we had a little more time, any questions? Any pressing questions?
Maybe I can ask a question. So just trying to understand the error mitigation, especially the post-selection. If I remember correctly, right? So the post-selection is being done on two different things. So one is the ancilla, right? So the ancilla is supposed to be on a 0 state. So you post-select based on the ancilla, but you also post-select based on the number of excitations.
Right. So okay. So I didn't go into those details, but it's good to mention. I kind of swept that under the rug. But okay. So in these distance plots, in order to easily define the distance between two excitations, what we do is we only select bit strings that have two plaquette flips. And this is okay, so maybe reasonable because these plaquette operators are not the particle operators of the system, but they should be close approximations as long as you're far away from the phase transition. So in general, there are going to be some dressed operators, but the approach here is just to say, okay, those dressed operators are going to have a large overlap with the single plaquette flips. So if we just measure the single plaquette flips where we have two plaquette excitations, the distance will probably be similar to if you measured the true particle operators. So that's kind of this two ancilla post selection. It's really just a technique or two excitation post selection. Sorry, it's really just a technique in order to unambiguously define this distance.
Right.
But on the right, what I'm showing here is data without this two particle post selection. So if you're looking through the paper and you don't want to read all the fine text, the the only time that I'm doing this two-particle post-selection is when I'm presenting distance. And at all other times, you know, I'm showing without that post-selection. And here, when we look at the raw data, we even see the signatures of confinement. You get other excitations popping up because, yeah, indeed, this plaquette flip is not an exact symmetry.
Okay, makes sense.
But that's right. So the main effect of you know, this post-selection here, you know, it's a factor of like several thousand, 10,000 maybe, between the total number of shots and the number that we're actually post-selecting, like 1 in 10,000. When we additionally do the two plaquette excitations, this is maybe a factor of 10 at most, or 5. So in terms of the error mitigation, most of the legwork is being done by this post-selection on the ancillas. And then when we go to two-particle excitation, it's, you know, it's much kinder, at least on the system size.
Yeah. Thanks.
Awesome. So how about we draw the group meeting to a close? Thank you for joining us, Tyler.
Thank you very much.
Okay, so I'm going to stop the recording now.